Thankfully, finding the mean or expected value and the variance when you're working with continuous data is really not too much harder than when we're working with discrete data. Now, I've put both types up here so that we can compare the similarities and differences. We've already learned how to work with discrete data, so we probably don't need to learn this from scratch. We really just need to see how it aligns. Now, when we're working with discrete data, remember we take each score, we multiply it by its probability, we have a whole heap of rows, and then we add all of those together, and that gives us the expected value. Well, don't forget that when we find integrals, really we are taking the sum of a whole lot of little rows. And so effectively we're doing the same thing, but the notation is different. And obviously action is different. With this one, we're going to make a table and line things up and calculate a whole bunch of things. Here we get to do some integration to do the same job. So have a look at the two formulas. We take x, here we multiply it by its probability, here we multiply it by f of x. Now that's the PDF, isn't it? That is the probabilities. Literally, that is a function that means the same thing as this. So that makes a lot of sense. Now dx is only on the end because when we're integrating, that's part of the notation that says integrate this stuff here. So if we understand this formula, we should be able to use the same idea here and remember what to do. Now the variance has what we called Formula 1 and Formula 2. So the first formula and the second formula are both on your reference sheet, and they're on your sheet like this, looking like the black version. The expected value of x take away mu, and remember mu is just another notation for the same thing, the mean or expected value. You have to subtract each score from the mean, or the mean from each score, square them, and then take the expected value of that. Now, to use this formula on the reference sheet, you've got to remember what the expected value means. That means multiply these things by their probabilities and add them together. The other formula, the second one, is usually easier to use, and that's because if the mean is some awkward number that's not a nice whole number, then your calculations get really complicated here. You can end up with a massive table full of really messy stuff that takes a long time to do. So finding the expected value of x squared, or each score squared, and of course to find the expected value of something, you find the x squareds, and they're often quite easy because often we're squaring whole numbers there. We multiply them by the probabilities and then we add them up. That's what take the expected value of x squared means. And then at the end, tacked on like an afterthought, we subtract mu squared, and that's there too. Well, these same two formulas have tons of similarities. We are again taking the integral, and that's because here, if we're going to sum up some things, then taking the integral is summing up. Now we're again doing each score minus the mean, squaring them, multiplying by the probabilities, which in this case is the PDF or little f of x. And then we just integrate them because that's our way of summing up. So if we understand how this formula comes from this one, then the way that this one comes from this one here shouldn't be too much more of a stretch. Now, just as with discrete data, the second formula is usually the easier one to use, I would recommend the same thing here with this one. So I have a box around this and a box around this. You can put it around both formulas if you'd like to have the choice. I tend to just use the second one every time. Now here, let's compare. We've got x squared, same, multiplied by the probabilities, same, except it's not p of x, it's f of x. And then we take the sum. Well, that's the same thing as integrating from the lower to the upper bound. Then at the end, after we've done all that, as an afterthought, we subtract mu squared. Now, don't forget that the standard deviation is just the square root of the variance. So once you've found your variance, take the square root and you'll have it. Now to practice, let's use that same example we've seen a number of times now of the chook wandering around in its enclosure that has a 6 metre radius. We already found that little f of x, or the PDF, was x over 18, and x had a natural domain of 0 to 6. So to find the mean distance that chook would be from the centre of the pen at any one time, we just write this formula. Now, with any formula that's new to you, I recommend writing out the formula at the start of each question before you do any subbing in. That way you get used to writing it and it goes in. So write the formula, we need x multiplied by the probability, and we need to integrate between our bounds. Next we can sub in our bounds of 0 to 6. We've got x multiplied by x on 18, so that's going to give us x squared on 18. Now you've got a choice when you're integrating. If you've got a constant there, you can always bring the constant out the front of the integral, or you can leave it there, it's up to you, because of course when you integrate x squared, you're going to get x cubed on 3. So if you've taken the 18th out the front, once you get your x cubed on 3, you could actually bring the third, or the over 3, out the front as well. And 18 threes are 54, so with this sort of method I can see that I'm going to get x cubed, but I'm going to have 1 on 54 out the front. Now if you choose to leave that 18 there, that's totally fine, the answer will work out the same. When we integrate this, we need to add 1 to the power, that makes it x cubed. We need to divide by the new power, so that gives us a 3 down the bottom, and the 18 that's there needs to stay there. So obviously 18 threes gives us that 54 that's on the bottom. So whichever way you prefer to write it is completely fine. You might keep it together, get to here, and then bring the 1 over 54 out the front so it looks like this one. It's up to you. Now when you sub your 6 in, 6 cubed is 216. So we get 216 54ths, which works out as 4, minus 0. So that means the expected value is 4. So when this chook is walking around this pen that has a 6 metre radius, if you wanted to find on average how far away it is from the centre, on average it's 4 metres from the centre. Now looking at the variance, I've chosen to use the second formula because I just find it much easier. We need to write I've broken my own rule. Let's write the formula first. We'll put the bounds. We need x squared multiplied by the probability. We need to integrate that and then subtract mu squared at the end as an afterthought. Now make sure that you're not finding the integral of this whole thing. Okay, so this section at the front here, you could ideally have brackets around it just to remind you that this minus mu squared is quite separate and happens after all of that. Alright, so subbing in our bounds 0 to 6, we've got x squared multiplied by x over 18. Now that gives you x cubed over 18, and just as we did over here, you could leave those together, or you could bring the 1/18th out the front. I chose to do that because I can see that when I integrate by x cubed, that's going to be x to the power of 4 over 4, so I chose just to leave it that way. I could at this point even bring that quarter out the front and find 18 times 4 and put it there, but I've chosen just to leave it like this. Again, there's lots of choice. Now, I've already found mu, that's the expected value. So you need this to find this. So whether or not your question asks for expected value, you need to do that first. So I've put in 4, and 4 squared is 16. Now subbing in my bounds, 6 to the power of 4 over 4 is 324. And then I subtract the subbing in of 0, which just gives me nothing. And then 324 divided by 18 is 18, so I end up with 18 minus 6, which is a variance of 2. So that means the variance of any of the positions that the chook could be in from the mean is 2, and that would be 2 metres because that's the units that we're working in. Now if you want to find the standard deviation, just take the square root of the variance.